Hello, AP Calculus students. Mr. Ford here with another quick homework tutorial. I say quick, this one might be a little longer, but I know we're going to skip a bunch of problems. We are going to skip 6-1-20. I know that for sure, starting the problem off. We're going to skip that one. We're also going to skip 125 for sure. Do not care about that graph too much. And we're probably going to skip a few other ones along the way. I'll point those out as we go, and I'll put them in the title of this video, which means if you're watching this, you probably already know which ones I'm going to skip. It's a cool little time vortex that you're in. Let's start with 118. Without a calculator, we got to evaluate some integrals. These are definitely must-do problems. So we're going to see these on pretty much every homework set from pretty much now on. Question A is going to go, actually, you know what I'm going to do? I'm going to try an interesting exercise for this. I'm going to write down the answers off of the published answer guide that I have right here in front of me, 65 1/3 for C, e squared plus 1 over here, and pi over 2 for this one. And then what I'm going to do is I'm going to use the published problems to write them over here. So let's start with problem A. Problem A is going to give us the integral from, I got to look it up real quick, negative 2 to 1 of 10x minus 3 times dx. What you're going to do now is you're going to find the antiderivative by using the anti-power rule. That gives us 10x squared over 2 minus 3x. That's it, yeah. That is the antiderivative. That'll work. Of course, 10 over 2, you can simplify that to be 5x squared minus 3x. And we're going to evaluate this from 1 to negative 2, which is pretty easy to do. In the first chunk, we got to plug in 1 for x. And then in the second chunk, we got to subtract, and we're going to plug in negative 2 for x. And we're just going to carefully work our way through this without making any silly math mistakes. This first block is going to work out to just be 5 minus 3, and that's 2. Second block will take a little bit more work to think about. Negative 2 squared is 4, and 4 times 5 is 20. And then 3 times negative 2 is negative 6, and that's plus 6. So what we've got here is 2 minus 26, which is, oh, and phone call in the middle of the lesson. Here we go. This is Mr. Ford. Oh, okay. 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 Well, I'm recording AP Calculus video right now, but I'll be done probably. I'll check it out before I leave. I don't know if you guys will still be there. But where is it? I can. Okay, cool. Thank you. Yep. Bye. Hey, neat. All right. Anyway, we get 2 minus 26, which is negative 24, which is what the answer guide said the answer was a little while ago. Pretty cool. Okay. Let's look at the next one, which is a trig one, which is always fun. Integral from 0 to pi over 3. Let's not let these things scare us. Secant of x times the tangent of x dx. This is the antiderivative. Let's see. Then secant x and tangent of x, that's the derivative of the secant of x. So the antiderivative of this is just the secant of x. And we're going to evaluate that from pi over 3 to 0. Now that can be kind of tricky here because we do have to think about what the secant of pi over 3 is and what the secant of 0 is. So it might be helpful to think about a unit circle really quick and just kind of ponder some of the angles. Actually, I withdraw. Let's just think about the first quadrant since this is only pi over 3 and 0. Since secant is equal to 1 over the cosine, I'm going to write that as 1 over x in these problems here. The secant of pi over 3, which is this angle here, the x value on this problem is 1/2. So in that case, that is 1/2 square root of 3 over 2. So the secant of pi over 3 is just going to be 1 over 1/2, which we could write as 2 in just a moment. And the secant of 0 is going to be 1 because this is the point 1, 0 right there. So this is 1. And so what we're going to end up having here is 2 minus 1, which equals 1, which is what the answer guide said it was a minute ago. See, pretty cool. Cool. Question C is going to ask us to do the integral from 9 to 25 of the square root of x dx. One of my favorite integrals here. I would prefer to think about this myself as the integral from 9 to 25 of x to the 1/2 power dx, which will make it a little easier to fit into our usual reverse power rule scheme that we saw a couple homeworks ago. In this case, it's going to be x to the 3/2 power divided by 3/2. Now, I normally don't write this, though. I'll write 2/3 times x to the 3/2 power, like that. Because dividing by 3 over 2 is the same as multiplying by 2/3. Believe me that the sooner you can start doing these things in your head, the better you'll be off. But we're just going to plug in 25 and plug in 9 to this. It's not going to be too terrible because 25 and 9 are perfect squares. So 2 times 25 to the 3/2 power over 3 minus 2 times 9 to the 3/2 power over 3. We'll try to simplify this as much as we can before going to a calculator if we need to, but we won't. Over on the left, 25 to the 1/2 power is 5, and 5 to the 3rd power is 125. And so we have 2 times 125 over 3. Over on the right, 9 to the 1/2 power is 3, and 3 to the 3rd power is 27. So we're going to have, let's see, is there a way I can think about this better without using a calculator? Man. What did the answer say it was a minute ago? I want to make sure I'm going to be on the right path. 65 and a 1/3. That sounds about right. I guess, I'm just going to muscle it. It's 250 over 3 minus 54 over 3. And that is going to be 196 over 3. I like that answer better than the answer that they have. I think it's 65. At this point, I'm going to break and use a calculator. 196 over 3. Yeah, it's 65 and a 1/3. But I like this answer better. I always have. That's a 3 and a fraction. Okay, let's look at the next question. Question D. I'm using a lot of space for these. I kind of recommend that you do the same. Okay. This is the integral from 1 to e squared of the natural log of x. A very easy antiderivative. Actually, or is it? The antiderivative of the natural log of x. What thing has a derivative of the natural log of x? Because I know the derivative of 1 over x is the natural log of x. So, well, let's see. When I take the derivative. Let me Google something really quick here. I'm just kind of blanking on this. Antiderivative. I'm sure it's something really easy. Oh, good golly. Skip D. Skip D. Skip it. D's out. You already knew that when you watched this video. You knew that already. You get to watch me puzzle over it for a little bit. No, this is dumb. Not on the AP test. It's the BC question, so we're not going to worry about it. E, though, is totally within our grasp to do. E is totally doable. I should edit these later on, too. But that would be too much work. E in this case is, I got to find my list of problems again. E is the integral from 0 to 1 of 1 over the square root of 1 minus x squared, dx. In this case, we just need to recognize what this is as far as a derivative. That is the derivative of the inverse sine of x. So this is simply the sine inverse of x, evaluated from 1 to 0. Now that itself can be kind of a challenging question to answer because the sine inverse of 1 minus the sine inverse of 0 is also a thing we really got to think about. Remember, let's just think about a unit circle. First of all, this is advanced pre-calc or trig, but sine inverse only really exists on the right side of the circle, which is not a thing I expect you to have memorized, but it helps if you do. What we're looking for is the angle that gives you a sine value of 1. And keep in mind that on the unit circle, the sine is just equal to the y value. So that would be this angle right there, which is pi over 2. That's the first one. And the sine inverse of 0 would be this angle right there, which is just 0. And that's why the answer is pi over 2. I really got to think about the antiderivative of natural log of x. I'll have to think about that a little bit more. Okay, let's move to the next question. We've been here for a while. That's pretty typical. 6.119. The graphs of the equations x equals y squared, x equals y minus 1, y equals 2, and y equals negative 2 are shown at right. These four curves form that region. We want to show that the area of this region is 28 over 3 units squared. So the hint given to us is to use horizontal rectangles, which we absolutely should do, because vertical rectangles would be a complete effing nightmare. I almost said the swear word there. Because the thing is right about this point, the functions start switching up into different chunks. It's much easier to divide this into horizontal rectangles, because each horizontal rectangle will be a consistent subtraction problem. It will be the integral from -2 to 2, because that's our boundaries, -2 to 2, of y squared, which is always on the right side, minus, what's the other function? Y minus 1, in parentheses, please. dy. We're using dy here because we're using horizontal rectangles. dx would mean we're using vertical rectangles. We can evaluate this integral any number of ways. You could take the antiderivative and get y to the third over 3 minus y squared over 2 plus y, and you could evaluate that from 2 to -2. However, I'm just going to use the calculator for this because I'm already over this problem, and honestly, on the AP test, you're probably just going to be asked to set this up. You probably will not be asked to evaluate it, just set it up, or maybe choose it from a list of multiple choice options. Let's let the calculator handle all the heavy lifting from here on. -2 to 2. We have to use x because the calculator can't handle it. Oh, my lights just went off. That's a good sign. X minus 1 in parentheses like that, dx. And it's going to be that number, 9 and 3 repeating, which is the same thing as 28 over 3. So we get 9 1/3, which is equal to 28 thirds. So I guess we've proven it, but we did it with the calculator. Next question. We're not going to be doing 6/120. Although it's a pretty easy question. We're not going to do it anyway. 6/121. We have a graph over here. We're asked first to state the domain and the range of this graph. So let's think about it first. The domain. We scan this graph from left to right with a vertical line. It would look like the leftmost point is -7, and the rightmost point is 6. And I believe every point of discontinuity is accounted for along the way. So the domain is all of the numbers from -7 to 6, like that. The range is going to be very similar. The lowest number that I see is -3. And scanning with a horizontal line all the way to the top, I see that 6 is the biggest number, but it's not represented because there is an open circle there. So I would say the range is from -3 to 6 with a round parentheses there. That'll help differentiate our answer. So where is the function continuous? Let's see. It's easy to start with the domain and then eliminate where it's not continuous. You know, I like the answer of where it's not continuous, but we'll answer the actual question. It is continuous only. It's not continuous only at 2 points. -1, which happens right there, is a jump discontinuity, and then at 4 there is a replaceable or removable whole discontinuity. So it's continuous from -7 to -1, and then it's continuous again from -1 to 4. And then it's continuous again from 4 to 6, which I think was the highest point we saw. Yeah, that'll work. The question that I have is, should those be round parentheses or square? I believe they're square. Nope, they're round. Oopsie poopsie poops. Oopsie whoopsie poopsie moops. Those should be round parentheses. I apologize, my guys. That's okay. Where does the function appear to be differentiable? I would say the exact same answer, honestly. The only thing that causes non-differentiability to happen is if we had a sharp corner, which I don't see on this graph, or a discontinuity, which we already kind of know. So it's going to be the same answer. -7 to -1, -1 to 4, and then again from 4 to 6. But at x equals -1 and x equals 4, you have discontinuity and therefore non-differentiability, because in order to be differentiable, you must first be continuous. 6/122 is going to ask us a bunch of limit problems about this, so let's get to it. The limit as x approaches -1 of g of x. Let's see. -1 from the left, specifically, of g of x. Well, -1 from the left looks like it's approaching a pretty solid 1, 2, 3, 4, 5, 6. This problem. Of course, if I approach -1 instead from the right on g of x, we're coming down here. That's a pretty solid -3. But because those two questions are different answers, this one, the overall limit with no from the right, no from the left, this one does not exist because they're different answers. The limit as x approaches -5 totally exists. -5 is a boring point on the graph. It's right there. Looks like it's 3 to me. The limit as x approaches 4 from the right is 2. Looks like as we approach 4 from the right, we're approaching a y value of 2. And the overall limit as x approaches 4, I believe, exists because it's also approaching 2 from the left. So I think this is also 2, even though g of 4 is actually 5, which is this point up there. That doesn't matter when it comes to limits. Limits only care about behavior. And since they are approaching the same thing right there, they are approaching 2, even though the actual point is 5. In this case, it might be worth noting that the limit as x approaches 4 of g of x is not the same thing as g of 4, which is why it's not continuous. They didn't ask us for that, but I'm going to point it out anyway, because we should point it out. Let's move on to a different question. On the next page, 6.123 says, trace your distance time graph and tangent t equals 1 second on your paper. Distance d is measured in feet. I think what's important here is I think they made a typo, because I think this is a distance graph, and I think they wrote v of t up there. I think that's a mistake. I think this is d of t, so I'm going to cross it off and write d of t above there. I think that's what's supposed to be there. Now our question, the first question, is to estimate the velocity at t equals 1. And so since we've got a distance graph, what we're really doing is estimating the slope of that graph at t equals 1. It's kind of up to you how you want to do this. I personally draw a little slope triangle like this and kind of hope that I can get some nice even numbers out of it. I don't know. It's going to be a guess no matter what. This looks to me to be about 4. This little side is like 3.5. So it's a little bit more than 1, I think, or so. Maybe. I don't know. The book says it's about 3. I disagree with that answer, but I'm trying to think of how they might have gotten it that way. But 1, 2, 3, it's probably a little bit more. Anyway, I'm getting about 1.5, I would say, for the slope. It does not matter that much. I'm just kind of guessing what it is. We're just estimating what the slope of that line is. Now, here's the important question. We're going to need a ruler for this, which is helpful because I have one on my tablet. We'll do this exercise tomorrow in class. We're going to locate another time on the graph where the object has the same velocity. Now, since the velocity on a distance graph, let's just think about this as the slope. At t equals 1, and use your graph, use ugraph, look at you, CPM, look at you go, to show how you know the velocities are equal. Well, here's what I'm going to do. I'm going to take this slope right there using my ruler, and I'm just going to kind of move along the curve until I find a point where I have that same tangent happening, which looks like it's happening right about there. I would say that tangent happens along that curve right there. So I think right there or so is where I have another point where the velocity is exactly the same. It's a little bit more than 4. I would say 4.5 or so. But the reason why I know is because the lines are parallel. If you think about it, on this distance graph, 2 parallel slope lines are the same velocity at the same time. That's important. Let's talk about probably the most bulky question as part of this homework is 6.124. I can tell you right now that we are probably not going to do part B. We'll see how long. Actually, no, we are going to. I apologize. I immediately withdraw. The first question is too easy anyway. How many tangent lines exist at x equals -2? Again, it can be helpful to get out a ruler and maybe draw a vertical line. You know, they could have picked another spot where it's a little more clear, but hey, it is what it is. There are going to be 2 points that we're looking for here, 1 and 2. Let my tablet catch up with my work here for a minute because it's a little bit behind. It'll catch up in a moment here. There's 2 spots where that vertical line is going to touch the graph in question. There they are. Hey, we did it. Now the question here is we want to write the equations of the tangent lines at x equals -2. Now that's tricky to do for a lot of different reasons, and this is going to take a lot of time. So I think we're just going to write one of them. I think that'll be fine. We got a lot of work to do here. Write the equations of the tangent lines. Now it's not too much. It's not too much if you think about it. But whenever you write the equation of a tangent line, you're just thinking about point-slope form. I never want you to forget this. It's a really easy formula. The problem is that we need to know the point and we need to know the slope. Now, we were just told the only part of this that we currently know is that x is -2. So the point involved is -2 comma something. The other thing that's challenging is that there's 2 such points. To find those coordinates, what we're going to need is the original function, which is x to the third equals 5xy plus 2y squared. We saw a problem like this on the quiz I gave you guys today too. What we're going to do is we're going to plug in, we're going to evaluate this when x is negative 2. What's going to happen here, we're going to get negative 8, negative 2 to the third power. We're going to have, on the right side, 5 times negative 2 is negative 10y plus 2y squared. What we've got now is a quadratic equation. We can do a little bit of simplification. We can move that 8 over. We can clean things up a little bit, arrange the parts the way we're used to seeing them. We could even divide everything by 2. And luckily, I was really worried that we were going to get a problem where we couldn't easily factor it either. In this case, you can factor it into y minus 1 and y minus 4. And that means that there are 2 corresponding y values. One is equal to positive 1, and one is equal to 4. So the 2 points in question are y equals 1 and y equals 4. And yes, in theory, we would have to do a line for both of them. As if that wasn't enough, this is just the points that we're looking at. These are the coordinates of those 2 points that are on this drawing. One of them is negative 2, 1, which is not a very good drawing, I guess, and this is negative 2, 4. Right there and there. The other part is we need to figure out slopes. We haven't even started talking about derivatives yet. So let's go to the derivative zone. And we're going to need to do an implicit derivative here because we have dy dx's involved. So we're going to have 3x squared. We have a product rule in this problem. Oh my god. Where 5x is still 5x. The derivative of y is dy dx. Plus the derivative of 5x, which is 5 times the original y. And then finally, we're going to have plus 4y times dy dx. So it's not, on top of that, it's not even a very fun implicit derivative to do anyway. But we're going to soldier forward because we've already invested this much time in the problem. So let's go ahead and gather together all the dy dx's on the right side. We'll move everything that's not a dy dx over. So we'll keep 3x squared and negative 5y over on the left side. We're just going to move that term right over. And let's go ahead and pull the dy dx. We'll factor out those parts too. It'll be 5x plus 4y. A lot of times when I'm solving these problems, I do these steps at the same time. There's a lot of algebra going on here, but hopefully at this point you're a little experienced with this where you can move things around pretty easily without showing every single step. The final thing here is that dy dx is equal to 3x squared minus 5y over 5x plus 4y. And we need to evaluate this. We need to figure out what the slope is when x is equal to negative 2. Which, once again, is going to give us a quadratic equation with 2 answers. So let's plug forward. First part, we have 3 times negative 2 squared. That's going to be 20, negative 2 squared is 4. That's 12 minus 5y equal, or over, 5 times negative 2 is negative 10 plus 4y. And again, what we want to know is what is the slope. Oh, shoot. I withdraw. Sorry, I got to go back a step. I apologize. We actually know what the coordinates of the points are. That was the whole point of this thing. So we got to do this once for when it's negative 2, 1, and again for when it's negative 2, 4. So let's try that. Let's start with negative 2, 1, which will give us 12 minus 5 over negative 10 plus 4. In other words, 7 over negative 6. That is the first slope, or negative 7/6. The other slope that we're going to need is the dy dx when we're at the point negative 2, 4, which is the other point we identified that's on this line, or the other point where there's a vertical tangent or whatever, when x is negative 2. This will give us 3 times negative 2 squared again, which is also 12. This time minus 5 times 4, which is 20. 5 times negative 2 is still negative 10. This time plus 4 times 4, which is 16. This is going to give us negative 8 over 6, or negative 4/3. So, bringing this all the way back over here, at the point negative 2, 1, the slope was negative 7 over 6. And at the point negative 2, 4, the slope was negative 4/3. We can put all of this information together now to actually write the equations of those lines. The first line will be something like this. Y minus 1 equals negative 7 over 6 times x plus 2. And the second line, which I will circle in red here, will be y minus 4 equals negative 4/3 times x plus 2. We're going to exhale a deep breath. We did a lot of work in this problem, but if you zoom in, the steps are pretty straightforward. A lot of the work got really bulky, but the steps are pretty straightforward. You have to plug in the x value they gave you to find the y value. That's your point. And then find the derivative and plug the x value in to find the slope. In this case, we had x and y values because it's an implicit derivative, but for the most part, this is a good problem to see. Anyway, let's do one more. Let's do a 6-1-26 really quick. This will be the fastest problem on here. We're just taking the derivative. Oh, we're not going to do part B. Bop, bop, bop. That one's out. Part B is a dumb question, and I hate it. But part A is very easy and simple to do. In this case, f prime, capital F prime of x. All we have to do is take this x squared and plug it in for t, because we're taking the derivative of an integral, and that's going to cancel out. Cosine of the natural log of x squared. However, we also need to multiply by the derivative of x squared times 2x. So, that's 2x cosine of the natural log of x squared. Hey, we got out of here in under 30 minutes, which is better than I expected. Cool. We ended up skipping a bunch of stuff. I'll put it in the description. You guys are awesome. Thank you for making it so far. You're doing great. I'm so proud of you. Keep it up. I'll see you in the next video.